Welcome to the LemnaTec Academy. This is the third video of our mini-series on root analysis. We will look into some more complex analysis to count crosses and roots and to determine how the root density changes with steps. So let's get started. The next thing we are going to look at is the root density differentiated by depth. In preparation, I have to rearrange the grid a bit. First, we have to transfer the binary image of the skeleton using a loop-through device. Next, we need to add an area distribution maker device from the region of interest group. This device will divide the image depth-wise. First, select how many depth sections we'd like to consider. In this example, I take 11 subsections, numbered from 0 to 10. Then we arrange the enclosing rectangle such that it covers essentially the whole soil area. If we zoom in, we can now see the divider between the regions. If you want a finer resolution depth-wise, you may choose more of these sections. At this point, we need to convert these sections into distinct objects with the region of interest label attached to them. If we've done so, we can measure the bundles of root in each of these depth layer objects. In order to achieve this, we will have to do some trick. First, we use two universal converters to convert the complete region to one image object. First, we convert it into a binary image. Then we convert it into an image object list. Now we split this up using the image object's region of interest filter with the areas as regions of interest. We use the Cut Image Object Region of Interest option to do so. We have now 11 objects, each representing one level of depth. If we check the region of interest affiliation, you notice that the regions are counted bottom to top. This is something we should keep in mind. Now we have these 11 image objects. We could now use a color classification device to determine the relative abundances of root and other stuff in each of these objects. Therefore, we need first to convert the binary image into an RGB image. Here we redefine the two default color classes. one for the root, and the other class for the rest, including the background and soil. This way, we get the abundance of white pixels, aka root, in each of the regions of interest, which are our depth levels. Finally, we need to add the object CC region of interest writer. We can configure here two images the usual way. In the Objects List Output section, we can check the region of interest affiliation and the color class assignment. We can check these values in the Tool tab. Here we see only the absolute abundances of the two classes, but the output files will also include the relative values. Of course, these are influenced by the size of the depth regions. Now we get to a more special analysis. We want to count how often roots cross and how often they fork. Due to technical reasons, some crossing roots may turn out as two joints close to each other in the skeleton. However, sometimes there are really only two joints that happen to be close by. Therefore, there's some ambiguity and we have to define a threshold somehow. But let me show how that is done. First, we transfer the skeleton output of the skeleton extractor. We may use the sanitized skeleton of the skeleton interpreter as well. We convert this into an RGB image. Using standard colors, the pure joints appear in red and crosses in green. We can use a forward background separation to detect either of them. Next, we will expand them by, for instance, 8 pixels. Using this value, all joints which are closer than 16 pixels to each other will be considered a cross. You may change this value to match the requirements of your application. This is the aforementioned threshold. Now we will remove all normal joints from the joints signal. We use a fill areas device for it. In this device, we will remove all objects smaller than 8 plus 1 squared equals 324 pixels. This way, we keep only those joints which happen to be close by. As explained earlier, we will consider them crosses. Now we have three signals: the real crosses, all joints, and the close by merged joints. In order to get the crosses, we can use the logic operations device with the OR operation and merge the crosses and the merged joints. Then we convert them into image objects. And merge them using the image object composition device. Finally, we write the results using an objects writer. This objects writer will provide the number of crosses in the sub-objects count column, as well as some morphological information about the distribution of crosses. In order to get the real joints, we invert the merged joints signal and combine it with the original joint signal using the logic operations device with the AND operation. This removes the merged joints from the original joints because the merged joints are not highlighted in the inverted signal. Then we do the same as for the crosses. So we have an option to count crosses and joints in our skeleton. This was the last video on root analysis with LemnaGrid. Feel free to ask us if you need further assistance. In the final video of the series, we will discuss some special considerations we need to take into account when we create analysis definitions based on the grid we created in this mini-series. See you there.